So in this second video on logarithms, what we're doing is we're using what we've learned in our first video to be able to solve equations and worded problems involving logs. Now, one way to spot these types of questions is if you are solving an equation where x is a power. So what we're going to do is we're going to continue with what we've learned on the basics of logarithms and see how we can go about answering questions where our variable or our x value is a power. So not only will we go through some quite simple looking questions, we'll also be going through some more wordy and more complicated multi-step questions like the ones here. Now, one thing I probably recommend that you do is either pause the video, have a go at some of these questions yourself, or watch the video and maybe in a couple of days have a go at some of these questions yourself and see how much you remember, because you can always go back and have a look at the work solutions, which is what we're going to go through now. So if you look at question one, our main objective is to, when we're setting up these questions, is to make sure that we've only just got a base number and its power on one side and everything else all on the other. So with question 1a, so if I just start by writing the question out again, and what we want to be referring this to is, if you remember the laws of log a x equals y, this is what we're wanting to do. So what I'm going to do is make a quick note of this because I will be referring to this. Now, what we're wanting to do is, when we start working and applying what y is, because obviously what we're trying to do is find the power, which in this case is y. I know in the previous example x was the power, but that don't make a difference as long as you've got it here. So what we're wanting to do is to get it in this form. So if we can try and get just the base number and its power on one side, we can then take the log and we can use this notation here to work out what it is by typing our log ax in our calculator. So from this, what I can then do is take the log of both sides. So that's going to be to the 9x equals log 28. Now if you think back to when we've got a power, I can move that to the front, so it gives me x, and I'm just going to put this in brackets, so log 9 equals log 28. And whenever we're solving the equation, we always want to make x the subject, so I take the log 9 over to the other side, so I get log 28 over log 9, which gives me an answer of, to 3 decimal places, of 1.517 to 3 dp. So moving on to question B, let's see if I've got a bit of space here. So again, very similar notation. So here our power is 5x, and that's equal to 40. So again, I've got base number and the power. It doesn't matter what that power is, but I've just got a single base number, a power on one side, so I can take the log of both sides. So I've got log 3 of 5x equals 40. Take the 5x over to the front, so I've got 5x, and I'm just going to put this log 3 in brackets, equals log 40. Now bear with me because I've seen a mistake as I am trying to multitask but failing. That should be log 40. And then we take this log 3 over to this side, so we get 5x equals, well, I can actually take, actually be better for me to take, if I rewrite this as x5 log 3 equals log 40. Now it doesn't really make a difference, but I'm just making it easier for me to type it into my calculator. So that's going to equal log 40 over 5 log 3. Let's just make that a little bit neater. Glad I've got a rubber. And if I type that into my calculator, I get 0.672 to 3 decimal places. So moving on to C. So here we've got, again, got a linear function as our power, but again, I've just got a base number and a power written like so. So I take the log of both sides, so I've got log 6 of x minus 2, I'm going to put that in brackets, and log 4. Then move the power to the front, so I get x minus 2, bit of lag, log 6 equals log 4. Now, some people would expand the brackets to this. I'm not going to bother because I just want to get x a subject, so I'm just going to leave it as it is. So I've got x minus 2 equals log 4 over log 6. Now, one thing that usually unearths a lot of students is the fact that we've got this log, and you don't realise that it's just it's like a function with a number. So it's very, very similar along the lines of cos, sine, and tan, where it only works when you've got a number next to it. And if you've got a calculator, and one thing I forgot to mention, that if you have got a calculator that only deals with where you've got this button, then obviously there's no bases mentioned in any of these questions, so just use the base 10. If you've got a button that's just got log, then it's already pre-programmed of having base 10, so it's not a problem. So from this, what we then not finished, so we've got x equals log 4 over log 6 plus 2, which gives us an x value of 2.774 to 3 decimal places. And let's just highlight these answers so you can see whereabouts they are. So for D, again, very, very similar sort of notation here. So for D, we've got 5, 2x plus 1 equals 10. So again, take the log of both sides. So I've got log 5 of 2x plus 1 equals log 10. Then take the 2x over to the other side, 2x plus 1 to the front, and which then leaves me, I'm just about to jump a stage, but I might do that later because it's become a bit tedious. And then we take the log 5 over to the side. So what I'm going to do here is, just to save a bit of time, I'm going to have got my log 10 over log 5. Now for this, I'm going to have to take away 1 and then divide by 2. So then from this, what I've then got is, now if I type this into my calculator, which I'm going to do now, so I've got log 10 divided by log 5 minus 1 divided by 2 equals, and it's going to be 0.215 to 3 decimal places. And let's just quickly highlight that answer. So moving on to E. Here now we've got 3 times 2 to the power of x equals 7. Now as you can see, I've got this 3 that I need to get rid of, because what I'm wanting on the left hand side is just the base number and the power. So I need to get rid of this 3 first, and I do that by dividing. So it's going to be 2 to the power of x equals 7 over 3. I can now take the log of both sides, and again, even though I've got a fraction, it's still a number, but I'm going to keep in its fraction form. Move the x to the front, and then x equals log 7 over 3 over log 2, which then leaves me with a final answer of 1.222 to 3 dp. Then moving on to our last example, which again, not last example, question F, the last question in this particular question. So here again, very similar to E, we've got 9 times 5 to the power of x equals 4. So I need to get rid of this 9 first. So I've got 5x equals 4 over 9. Take the log of both sides. Now, when you're working through this, feel free to jump stages, but just be careful of not making any silly mistakes while you do. I'm just taking my time so you can clearly see what each stage and what I'm actually doing. So then taking the log 5 over to the side, so I get x the subject, well 4 over 9 over log 5, which leaves me with a final answer of minus 0.504. So as you can see, you can get negative numbers in these questions. So moving on to question 2. So as we said, one of the main reasons of why we use logs is when x is a power. And solving these, unlike indices where I can't get my base numbers to be the same. So for example, I can't write 3 as a power of 2. It's going to be very difficult without going into fractions. But this is where logs comes into play. So this is how it's important you can differentiate between indice questions, solving equations involving indices, but also logs as well. And again, if you were to use a log question or an indice question, you wouldn't lose any marks for it. It's just, as long as it's a valid mathematical technique, it's going to be absolutely fine. So, going on from this with question 2. So as you can see, we've got base numbers and powers just by itself. There's no other constants in there. So what I'm going to do with regards to question A is I'm going to take the log of both sides. Now I'm going to put the power in brackets. Like so. Now at the next stage, what I then need to do is move the powers over to the front. So I've got x minus 1 log 2 equals x plus 1 log 3. Now if we expand the brackets out, so I get x log 2 minus log 2 equals x log 3 plus log 3. Now as you can see, we want to try and make x a subject. So if you think about rearranging the formula in terms of topics, when you've got x on both sides, we want to take everything with x's onto one side and everything else over to the other. So here I'm going to end up with x log 2 minus x log 3 equals log 3 plus log 2. Now again, there's no way of me simplifying this. It's not like collecting like terms because x is our coefficient, not our base. So what we can, the clever thing we can now do is factorize. So as both terms on the left hand side have got x, I can factorize it with respect to x. And so going from having two x's, I've now just got the 1. And now all I need to do is take the log 2, take the bracket over to the side by dividing. So x equals log 3 plus log 2, or divided by log 2 minus log 3, which gives me an x value of minus 4.419 to 3 decimal places. Likewise with regards to b, so here I've got, if I take the log of both sides straight away, and again putting your powers in brackets, sometimes it helps, sometimes not. It depends on how neat your work is. I'm going to try and encourage good presentation. So again, moving those powers to the front. We get this. And then expanding the brackets out, so we get log 6 minus x log 6 equals 3x log 2 plus log 2. Now for this, it makes more sense for me to take this x, negative x, over to the other side to make it positive, because I much prefer working with positives and negatives. And I'm going to take this log 2 over to the left hand side. So what I end up with is log 6 minus log 2 equals 3x log 2 plus x log 6. So then simplifying, or factorising I should say, the right hand side, so I get 3 log 2 plus log 6 with respect to x, and then I take the bracket over to the side, leaving me with log 6 minus log 2 over 3 log 2 plus log 6 equals, and if I type that into my calculator, I should end up with an answer to 3 decimal places of 0.284. So as you can see, there's quite a few steps, and however, these types of questions in an exam will usually carry probably about 3 or 4 marks maybe, depending on how much work you need to do. So it's important that you are doing things in steps, because you're not too sure what you're getting a mark for. So as long as it's implied in your working out, you're going to be absolutely fine. So moving on to question 3. Now question 3 can sometimes be represented in a worse way than what we actually need to do. Now as you can see, in terms of looking at some of these questions, they aren't the best, and it's quite difficult to clearly see what we're actually wanting to see, or what needing to see I should say rather. Now if I would say to you, when you're looking at these types of questions, you need to think quadratics, you might be thinking, right, I can somehow see a few powers, but not enough for me to think, right, this is a quadratic equation. Now, one of the reasons for this is the way that it is written, and it's important that we write these questions because, I'll be honest, there is no other way of doing this. So if I start off by writing the question out, and hopefully it will make a little bit of sense as to how this is potentially linked with quadratics. Now, what makes this question easier is, or easier to kind of see, is if I put brackets around these. Now, there is no other way of me writing 2 times 2 to the power of 2x. I can't combine the 2 times 2 to make 4 because only this 2 here, it has got a power of 2x, not this one here. And likewise for here, I can't do 22 to the power of x because only the 2 has got the power of x, not the 11. So another way of writing this would be to write it as 2 bracket 2 to the power of 2x minus 11 2x plus 5 equals 0. So all I've done is I've replaced the times with brackets, so it looks like this. Now if I then let's pick another letter of y equal 2 to the power of x, then what this then becomes is 2y squared, because if you think about it, if I just write a little bit here, so 2 to the power of 2x is the same as 2x squared, and so that's why it becomes y squared. So just get rid of that. And going back to this question, minus 11y plus 5 equals 0. So now, as you can see, this is now resembling a quadratic equation. So if I then go on and solve this, so I'm going to solve it by factorising, which it does. And again, you could go straight into the formula if you can't bother to think about factorising. So here we get a value of y equals a half or 5. Now, we've not answered the question because we need to work out what we've substituted. We don't want to work out the value of y, we want to work out the value of x. So what we've then got is 2 to the power of x equals a half, or 2 to the power of x equals 5. Now if you go back and look at what we did before, so if I take the log of both sides, so I take the log of 2, and I'm just going to jump a stage just because I'm running out of space. So x equals log of 0.5 over log 2. So in this particular case, x equals minus 1. Now in this situation here, I've got x log 2 equals log 5, so x equals log 2 log 5 rather, over log 2, in which I get an x value of 2.322 to 3 decimal places. So working with b, which I'll use a different colour. So again, I've got 2x minus 3 times 2 to the power of x plus 2 equals 0. So I'm going to leave this as, let's write this as 2x squared minus 3 lots of 2x plus 2 equals 0. I'm then going to let y, let's do that here, so let y equal 2x. Now it's worth writing in your solutions what you're letting y equal rather than just a random letter coming in. So it's important that whenever you work in solutions, it's easy to follow through. So just like I'm trying to make my solutions easy for you to understand and understand what I'm doing each step, it's quite clear and concise, obviously along with my commentary, but what you want to try and do is try and translate that when you're doing your work. So from this we've got y squared minus 3y, not squared, plus 2 equals 0. I then go on and see, does this factorise? Yep. So my two solutions are going to be y equals 2 or 1. So from this I've got 2 to the power of x equals 2 or 2 to the power of x equals 1. Well, I don't need to do any logs on this one. Well, I can, it doesn't really make a difference. But anything to the power, well, x must be 1 in this case because anything to the power of 1 equals itself. And x must equal 0 in this case because anything to the power of 0 gives you 1. But again, if I was to do the logs of both these two sides, I would have ended up with the exact same answer. So moving on to question C. So question C looks a bit more complicated. So actually let's start up here. So here we've got 2x minus 1 minus 5 times 3x x minus 1 plus 2. Now this one looks ridiculously tricky, and one of the reasons why I've purposely chose this question is because sometimes when you've got someone who goes through examples, they go through simple ones, and then when all of a sudden you get stumped on a difficult looking one. So hopefully A and B make sense, and let's have a look at what we need to do when we get a question that looks like this. Now there is definitely a little bit more extra thought that needs to go into this particular question. Now 3 2x to the power of 3 to the power of 2x minus 1. Now I can rewrite this as 3 to the power of 2x times 3 to the power of minus 1, because when you're multiplying you add the powers together, and 2x plus minus 1 becomes 2x minus 1. And likewise, if I had 3x to the power of 3 to the power of x minus 1, I can write this as 3x times 3 to the minus 1. So if that was a plus 1, then that would just be a plus. If this was a plus 1, then that would just be a plus 1. If it was plus 3, that would be a plus 3. So whatever this second constant is, whatever you're adding or subtracting, that's what's going to be next to your base number here. So what I'm now going to do is I'm going to substitute these two things here for those two brackets, and I'm hoping that I've not completely bodged up what this looks like. Well, let's have a look. So if I just call this one hashtag 1, this one hashtag 2, I'm going to swap this for that and this for hashtag 2. So what I've got is, if I start by writing the question out again, so what this becomes is I've got 3 to 2x times 3 to the power of minus 1 minus 5 lots of 3x times 3 to the power of minus 1 plus 2 equals 0. Now if you think back to what 3x to the power of minus 1 is, well 3 to the power of minus 1 is just a third. So what I end up with is 3 to the 2x divided by 3 minus 5 3x over 3 plus 2 equals 0. And so from this, now if I then multiply everything by 2, so multiply both sides by 3, just to get rid of the brackets, and the fact that it's equal to 0 doesn't really make a difference. So what I'm left with is 3 to the 2x minus 5 to the 3x, because obviously times in by 3 the fractions will cancel, plus, and then it'll be 2 times 3, which is 6, equals 0. So now what I'm going to do is, if I then let y equal 3 to the x, I end up with y squared minus 5y plus 6 equals 0. And again, if you're not sure where the 3 2x has come from, well, that's because I've rewritten it as 3x like so. So then that then becomes y squared. From this, I can then solve this, so I get my two solutions as being y equals 3 or y equals 2. So then what I've got is I've got 3 to the power of x equals 3, or 3 to the power of x equals 2. Now in this case, x is just going to equal 1. However, in this case here, what I've got is I'll have log 3 and then move the x to the front equals log 2. So x equals log 3, log 2 rather, log 2 over log 3, which gives me an x value of 0.631 to 3 decimal places. So as you can see, when it comes to these types of questions, you'll never really escape quadratics. It's one of these things that always makes a return, and it's always important, particularly at A level. And although it's covered at GCSE that you're able to do it, but this just shows solving quadratics questions in a completely different form. So moving on to question 4 now. So now we've got logs in its more sort of customed itinerary. So looking at question 4, what we've got is this. So let's just scroll down a little bit more. Right, so with question 4, how we get started on this is going in the reverse. So what we're going to do here, so if you think back to that initial form of ay equals x, and that can be written as log ax equals y. Now what we're going to do in this particular set of questions is we're going to go from this form to that form. So what I need to make sure is, and that's exactly what we're going to be doing. So it's always worth just making sure that, again, the key thing with this is make sure you've got no number in front of your logs, make sure you turn it into a power, and then it's just a case of substituting numbers in. So what do I mean by all of that? Right, so looking at question A, let's start by writing the question out. So here we've got log to the base 10 of 2x minus 40, and that equals 3. So substituting this in, I know that this 10 is my a, 2x minus 40 is my y, and 3 is my x. So all I'm going to do is substitute those into this and I'll get the answer. But again, you want to try and get practice of understanding and how to read these questions to make it easier for you to go on and say. So what we've got is we've got 10 to the power of 3 equals 2x minus 40. That then becomes 1000 equals 2x minus 40, and then we just need to rearrange this, so we've got 10,040 equals 2x, so x equals 520. Then for B, we've got log 3 of x plus 2 plus log 3x equals 1. So what we need to do is we need to write this as a single logarithm. So write this as a single logarithm. I've got a plus, my base is the same, so it's going to be absolutely fine. So I've got log 3. Now when we are adding, it means we're multiplying, so I'm going to have x plus 2 x equals 1. Now that looks a bit odd only because of the way that a question's written, so I'm just going to rewrite this again just so it's a bit more apparent what we've done. And again, sometimes you can go a bit sort of bracket crazy, so again feel free to use square brackets. So what we've got is we've got log 3 of x squared plus 2x equals 1. We can then substitute in, so a in this case is 3, y is x squared plus 2x, and x is 1. So what we get is we get 3 to the power of 1 equals x squared plus 2x, which then slowly looks like a quadratic equation. So if I take this over to the side, I end up with 0. X squared plus 2x minus 3, which then factorizes like so, and then our two solutions are going to be minus 3 or positive 1. And now moving on to question 5, which is here. So from this, now again, this may not look like a quadratic, but we might need to do some manipulation. So again, quite difficult, not an easy question, but just something that hopefully by watching me and working through this problem with me, you'll have an understanding of what it is we need to do. Now with this, what we want to try and do is, I notice that we've got a 25 and a 5. So I'm thinking to myself, right, well let's write this as a power of 5. So what we get when we write that as a power of 5, well I'm going to get 5 squared x plus 4 equals 5, and then x to the plus 1. Now what I'm then going to do is I'm going to leave the left hand side to start off to begin with. Well, actually what I am going to do is I'm going to swap the x and the 2 around. Excuse me. And then what I'm going to do with this is, as we did in a previous example, I'm going to rewrite this as 5x times 5 to the power of 1. Like so. So this particular question looks a little bit more challenging, but one thing I noticed straight away is the fact that I've got a 25 and I've got a 5 as my base numbers. So if I start by writing the question out, correctly. Let's see. Equals 5x to the plus 1. So I noticed straight away that 25 can be written as a power of 5. So let's just start by doing that. And by doing so, what this now is slowly starting to look like, it's starting to look like a quadratic, very, very similar to the previous questions that we've done. So what I'm going to do now is I'm just going to swap the power on this left-hand side around. So I've got 5x squared plus 4 equals 5x plus 1. Now the next thing I'm now going to do is work with this. Now we've done this in a previous question, but 5x plus 1 can be written as 5x times 5 to the power of 1. And again, when you add the powers of x and 1, it's going to give you x plus 1, which then becomes 5x times 5. Now what I'm going to do is I'm going to substitute that bubble and swap that for there. So what we end up with is 5x squared plus 4 equals 5 to the x times 5. Now from this, what I can now do is take all of this over to the other side. So what I've got is, now another way of writing this is to write this as that. And so what I can then do, let's move it over here. So I've got 5x squared minus 5 lots of 5x plus 4 equals 0. And then if I let y equal 5 to the power of x, I get y squared minus 5y plus 4 equals 0. If I then go on and solve that, I get the values of y equals 4 or 1. And again, that does factorize. So basically substituting x back into it, so I get 5 to the power of x equals 4, or 5 to the power of x equals 1. Well, in this case, x is just going to equal 0. However, in this case here, I need to take the log of both sides, and if I've moved the x over to the front, so here I get x equals log 4 over log 5, so x equals 0.861 to 3 decimal places. So although this question didn't initially look like a quadratic equation, with a bit of practice, that's kind of thing you're thinking that you need to look at. So when you think of these questions, you think, right, okay, it's maybe in some cases it can involve a quadratic equation, so you kind of need to manipulate the question to make it easier for you to do just that. So moving on to question 6, the question reads, given that we've got log to the base ax equals log a to base 5 plus 2 log to base a3, where a is a positive constant, show that x equals 45. So what we want to do is show that question, so it's also looking at a proof question, and that's what we've got. So looking at this particular question, what we need to do is, now if I just start by writing the question out, sometimes it's a little bit easier to get more of an understanding of what it is we actually need to find, and also helps if you don't copy it wrong, like so. And we've got log a to the 5 plus 2 log a to the 3. Now when you're thinking about this, what we want to try and do is make one side look like the other. So here on our left hand side we've just got log a to the base x, and here what we've got is we've got a collection of logs that we need to do. So our sort of intention is to write this as a single logarithm. Now as the bases are the same, now when I write this as a single logarithm, as you can see here I've got x, so whatever I've got log a to the base of what, then that's what x is going to equal. So writing this as a single logarithm, I'm first going to start off by getting rid of that 2 first by turning it into a power. So I've got 3 squared, which then becomes log a to the 5 plus log a to the 9. And when we are adding, it means that we're multiplying, so I can rewrite this as log a to 5 times 9, which is log a to 45. Now if I bring this back down, so I've got log a to the x. Now as you can see, both these sides have got a log to the base a, so the only thing that's actually different is going to be the 2 brackets. So therefore, what I'm going to do is show that question. So here's our x equals 45, and that is what they've wanted me to prove. So moving on to a similar question in question 7. So here again, my main objective is to try and write the right hand side as a single logarithm. So again, start off by writing the question out. And again, how do I know this? The first thing that you always want to check is make sure that the bases of each of the logs mentioned in the question is the same. So in this, all my logs have got to the base a. Now, from this, I'm going to leave the 2 as it is. I'm going to try and simplify what's in the brackets first. So when we're taking away, we are dividing. So I get a, and it's going to be to the k over 2. And then this 2, as it's in front of the logs, can move to the turn into a power. So I've got log a to the k over 2 squared, which then becomes log a to the k squared over 4. Now if I bring this back down, so I've got log a to the x, as you can see that my x must be equal to what's on the right hand side. So here what I've got is I've got that x equals k squared over 4. Now looking back at the question, they want me to show that k squared equals 4x, so all I need to do is take the 4 over to the side, so I've got 4x equals k squared, and that is what they've asked me to prove. So moving on to question 8. So question 8, you may have resembled something that you've discovered, did at GCSE, which is looking at compound interest. Now at GCSE, what your teachers probably instructed you to do is to use trial and error, or randomly put years in to see whether you get a value of 15,000, well in this case would be 15,000. Now in this, what we're going to do is actually show you a more accurate way of getting through this. So let's have a look at this particular question. So it says the value of an investment of xi pounds after t years has a fixed interest rate of 4%. If £4,000 initially deposited with no further invest, after how many completed years would the value of the investment be worth more than £15,000? Now in this particular question, it's worth noting that there is how many completed years, and we want the value of more than 15,000. So if you think about compound interest, the general formula was that it was the initial amount, which in this case is 4,000, times by the decimal multiplier of the increase. So it's going to be 1.04 to the power of how many years, and I want this to be more than 15,000. So writing the question in sort of mathematical notation, it would look like this, and I would say that you probably get 1 mark for writing this particular step. Now what we want to try and do is solve this for t. So the first thing I want to do is take the 4,000 over to the other side. Now don't worry too much about the inequality, it doesn't really have much impact as to what we're going to be doing. Now I've got a base number and a power is equal to another number, so now what I can do is take the log of both sides. So I've got log of 1.04 t is greater than log of 15,000 over 4,000, and then I can take the t into the front, so I get log of 1.04 is greater than log 15,000 over 4,000, and then I take the log 1.04 over to the side, so I get t equals log 15,000 divided by 4,000, and I've made a mistake there, but not a big one. Let's turn that into an inequality, and that's all divided by log 1.04. So I get t equals, and if I type that into my calculator, I'm going to get an answer of 33.7 years. Now as the question's asked me for how many completed years, then it's going to be t equals 34 years. So after 34 years, that investment of £4,000 will become over £15,000. And one way to check your answer is by substituting 34 back into this initial line of working, and it should equal a number that's going to be greater than 15,000. Now just while I'm here, what I'm going to try and do is, let's say a question asked you to round this number up to the near, when it equals 15,000, give your answer to the nearest month. Now to do this, now we know we've got 33.7 years. Now to get this in months, if I take the decimal point, because I know there's 13 completed years, so 0.7 times 12, because there's 12 months in a year, is going to equal 8.4 months. So if I was asked to write this to the nearest month, then it would be 33 years and 9 months. As you find that. But this question doesn't, it just asks for completed years, so an answer of 34 would be the correct answer. So moving on to question 9. So slowly getting there. So again, this question says that a brand new car has a release price of £42,995 and has a fixed depreciation rate of 22% each year. After how many years would this car be worth £6,000? So the first thing you want to do is write this question out in some form of a calculation. So we've got the initial price, which is 42,995, times the decimal multiplier after a 22% decrease, which would be 0.78, to the power of t, which I was going to call it t. I want this to be worth £6,000. So not equals. Now if it was less than £6,000 and inequality would be going this direction, if it was more, well, not more than £6,000, it won't be a question, but there you go. But as it isn't, I'm just going to get rid of that. So now what we want to do is take the 42995 over to the other side, so we get 6,000 over 42995. I then take the log of both sides, and then if I take the t to the front, so I get log 0.78 equals that, and then take this over to the side, so I get t equals log 6,000. Now note how I've not reached for my calculator at all, and I'm using the exact values rather than any rounded answer, which is something that I certainly would recommend that you do. And then what we if I type that into my calculator, I'm going to get 7.926 to 3 decimal places. So t is going to equal 7.9 years. Now again, I could write this as 8 years, or if I wanted to write it in months and years, then it would be 0.9 times 12, which is 10.8 months, which we can round up as being 11 months. So if I really want to be accurate, it would be 7 years and 11 months. But again, that's not what's necessary. It's always worth checking the answer and seeing how they want the answer written. But I would say typically, if there's no mention of months, then just give your answer as years. So either 7.9 years if you want to be accurate, or to the nearest year, completed year will be 8 years. Now moving on to question 10, which is our last example, I'm sure you'll be glad to hear. So given that log ay equals 2 log a3 plus log a4 plus 1, and we're asked to express y in terms of x, giving your answer in a form that does not involve logarithms. So what we need to try and do is, if you think back to, let's not do that. So what we want to do is, when we had log ay equals x, and we had log ax equals y, so what we want to do is we want to write it in this form here, and that's basically what the question is asking. So initially we're going to work with this, and then when we get to when we write it in this form, we then need to convert it into this one here. So I'm just going to get rid of that. And so let's have a look at this question. So here what we've got is we've got log ay equals 2 log 3 a3 plus log a4 plus 1. Now, although I can work with this as being log a9 plus log a4, now the sneaky thing is that this plus 1. Now, in order for me to write the right hand side of a single logarithm, everything's got to be written as a log. Now, with regards to the 1, this plus 1 here, I can write this as log. Now, because we're dealing with base A, if I have log to base A of A, that's going to equal 1. So what I'm going to do is I'm going to replace the 1 with log AA. Don't have to put an equal sign there. So plus log A of A. And if I then join, as I'm adding, I've just got to multiply them all together. So it's log A of 9 times 4 times A, which then becomes log A of 36A. And if I drag this back down, I've got log A of Y. So what that therefore means is that as they're now to both sides are to log base A, that this bracket must equal this bracket, leaving me with y equals 36a, and there is our final answer. So hopefully the 10 examples that we've kind of gone through, you can kind of relate to any particular log question that you may be attempting, either in a textbook or in a test paper or an exam question. And so hopefully it gives you some form of understanding of what it is you can do. There are a lot of tricks to the trade and a lot of things to look out for, which is worth asking your teachers or trying as many questions as you can. And again, there is no problems with you being stuck. It's just a case of knowing what you can and can't do. And with a particularly brand new topic that you may never have come across, and it's a unique topic to A-level maths, it's going to be always that difficult to get your head around. Whereas with GCSE stuff, you've been doing it since at primary school in some cases. So this is something that's completely brand new. If you have any further questions or would like a worksheet to accompany this particular tutorial, then drop me an email at 162maths@gmail.com.